Well, good morning everyone. My name is Ryan, and today I will talk about the pore network model for the evolution of the pore structure during the fabrication of silicon carbide membrane, which made by chemical vapor deposition technique. So first I will give you a little bit of background of what I'm doing. My work is divided to two parts. One is the experimental work, which is the preparation technique of these membranes, and the second part is the simulation and modeling of this work. And then finally I will summarize my talk. So first let me give you a little bit background. As you know, in the recent year there has been considerable effort to make the membranes that are applicable for the high temperature purposes. The polymeric membranes that are available, they cannot withstand the high temperature, and silicon carbide with its special characteristic, it might be a good candidate for such application. So what are these applications? One of them is producing hydrogen. Hydrogen is an attractive fuel. It's a clean energy and it's flexible. So, and mostly it's produced by steam reforming reaction and water gas shift reaction. So, the first one is a steam reforming reaction, and the second one is the water gas shift reaction. So if you have a membrane reactor that can remove that would be perm selective to hydrogen, which remove the hydrogen from the product side, then you will get a higher conversion of hydrogen. And as you know, steam reforming reaction is an endothermic reaction, so if we can operate in the higher temperature, then we can even go to the higher conversion, so which is our purpose. But before we get to that application, we have to first find a way to make these membranes. We basically, and then even before making the membranes, we have to make the support for those membranes, because those are the really thin layer of membrane, and they have to have a support so they can be sit on and give a physical strength. These are the support that we make. These made of silicon carbide. These are the homemade support, and the good thing about this is that they're the same material as our membranes, and so in the high temperature we won't have any thermal expansion difference between the membrane and the support, so which is good for this application. So we've put this is the reactor that we make this membrane. Basically this is our CVD reactor. We put one of those supports here, and then we have our source for silicon carbide is a polymeric precursor, which is called triisopropylsilane. It's injected through the syringe pump. It preheated first to evaporate, and then it carried out by the argon into the reactor, and it goes to the reactor. Reactor function at we operate our experiment at between 700 to 800 degrees C. It goes there, it decomposes, and go to the pores and deposit it there and shrink it to the pore. So the pore is getting smaller and smaller, so we can measure the permeance of the gases that is coming out. So we did our test for two gases, argon and helium. So as you can see, as the TPS decomposes, it starts shrinkage the pore, and the pore is getting smaller. So helium, being the smaller of those two gases, can still access, while the pores are shrinking, it can still access the larger portion of the unplugged pore. So that's why the argon permeance decreases faster than helium, causing the selectivity of these two gases goes up, which is good. And in order to, so the next part of our job is that to model this phenomena, that means the shrinkage of these pores, how it happens, it goes through what reaction, and how we can study better the phenomena, and then we can optimize it and make the performance of the membranes better. So for doing that, we developed a three-dimensional network, which the pore radii of the network are distributed according to the pore size distribution that is generated by the computer, and is pretty matched by our experimental pore size distribution. We study the effect of connectivity of the pores, thickness of the network, and the effect of pore blockage also is taken into account. So the simulator can monitor the pore size distribution during the deposition of the triisopropylsilane. So in order to give you an idea how this works, this is our support, this layer right here. And we divide it in 3 parts. One is the tube side, which the reactant goes in, flows into the reactor. And then we have the shell side, which we measure the permeance. And we have the membrane section. So in the membrane section, we divided it, it's a 5 centimeter long membranes, and we divided it into a couple of grid blocks, and each of these blocks consist of a pore network which shaped like this, and each pore are connected to a node, and then the number of the pores that connected to each node is called connectivity. For example, for this case, the connectivity would be 6. So basically what happened, the reactant goes here, it goes to the pore, it decomposes and it reacts, and the pore is getting smaller and smaller as it continues. So before we start, we have to have a right pore size distribution for this model. So this is the equation that we use for the pore size distribution, which generates the pore size distribution, is the continuous line here, and it pretty matches with our experimental data, which we did for the support for the through the porometry technique. And so this is the initial pore size distribution that we have, and it's for the support. So membrane hasn't formed yet. So in order to let these things go in, we used the dusty gas model, which is the same as Maxwell-Stefan equation, and the pores shrink as the deposition continue, and since the pores are shrinking, the pore size are varying during the deposition. So what happened is that for each pore size, you have to use a different mechanism for the transport. So including viscous flow for the really big pores, hindered or configurational diffusion, and Knudsen diffusion, and we have to take all these 3 into account. So the material balance for our system would be the first 2 equations, which A stands for the triisopropylsilane, and it has the reaction term because that's the only component which is react. And we have argon, which is this one. As you can see, here is a non-steady state equation, but as you can notice, the amount of reaction and the amount of diffusion of the gases through the membrane is more than the change in the pore size. So we basically can neglect the change of the pore size with respect to the amount of that is diffusing. So we can do this equation as a quasi-steady state and cancel these first 2 terms. And then Rx is the reaction per unit volume of the component, and it can be related to the per unit surface because it first goes to the pore, decomposes in the volume of the pore, and then it reaches the surface and reacts there. So this is the equation for the reaction on the surface. And J is the total flux, which consists of diffusion flux, JD, and viscous flux, which is JB.